My talk is about the rotational spectroscopy that I used from 2007 when I started my PhD at the University of Valladolid. I applied this technique or this spectroscopy to the study of biomolecules, to the molecular structure of biomolecules, also to the study of molecules and reactions with atmospheric interest, like Krieg intermediates. And from 2018, when I joined the molecular astrophysics department or group at that time, I started to do rotational spectroscopy studies of molecules with astrophysical interest. Rotational spectroscopy is one of the most precise experimental tools to investigate the molecular structures in the gas phase. The rotational spectrum of a given molecule depends on the values of the rotational constants. These constants depend on the mass distribution that we have within the molecule, within the molecular structure. So the rotational spectrum can be considered exclusive for each molecule and is a fingerprint of a given molecule. So using rotational spectroscopy is possible to distinguish between the structure of different isomers, conformers in this case, tautomers like this, and also between isotopic species, even when the molecular chains or the structural chains are really small. Using different experimental approaches, we can observe the rotational spectrum in a wide frequency range that starts at the microwave region and go up to terahertz region, passing through millimeter and submillimeter regions. So we can observe the rotational spectrum of a large variety of molecules with the only requirement for the molecules to present a dipole moment different from zero. Probably the most important application of the rotational spectroscopy is that to the molecular astrophysics. This is because when we observe an astronomical object using a radio telescope, we can obtain a line survey or a spectrum where we can see all the rotational transitions of all the molecular species that are present in the object that we are observing. So the identification of all the molecules that are forming this object requires the accurate knowledge of the frequencies of all the rotational transitions for this species. We can obtain this information if we do rotational spectroscopy experiments at the laboratory, where we can study and we can obtain the rotational spectrum of a single molecule. And then, with the help of the quantum chemical calculations, we can identify and assign every single line, every rotational transition. And then, after the analysis with a Hamiltonian, we can derive the molecular parameters of the molecule that we are observing. These parameters are the rotational constants, the centrifugal distortion constants, and also hyperfine constants, depending on the molecule that we are considering. If these parameters are accurate enough, we can get predictions in the same frequency range that we are observing with our telescope, and we can directly compare both spectra. Comparing by the direct comparison, we can identify one by one each molecule in this object. around 95% of all the molecules discovered in the interstellar in the space have been identified using this methodology. My research in the institute from 2018 develops in the context of rotational spectroscopy and molecular astrophysics. And my research activities are summarized in these 3 points. On one side, I do rotational spectroscopy experiments using the Gazella experimental setup that I will show in the next slide, of molecules that are candidates to be detected in the space. In a second type of experiments, I try to generate and characterize, using rotational spectroscopy, different unstable species with astrophysical interest. This part of my investigation is done in collaboration with NYCU University in Taiwan, in particular with the laboratory of Professor Endo. And another part of my investigation is dedicated to the detection of new molecules in space using quantum chemical calculations. Well, Gacela, that means gas cell for laboratory astrophysics, is an experimental setup that was built in the Cabezas Observatory in 2017-2018 under the context of the European project Nanocosmos. This experimental setup is dedicated to the study of molecules and molecular processes using high-resolution broadband rotational spectroscopy. The design of this experiment is very new because it was the first laboratory experiment that used the same receptors using the radio telescopes to detect the molecular emissions in a laboratory. The design is the one shown in the pictures, and the experimental setup consists of a vacuum chamber that is almost 900 millimeters length and 50 millimeters diameter. This chamber is connected to a vacuum system that is formed from a scroll drive pump and also a turbomolecular pump. And in this part, we have the two receptors in the Q band and the W band. And in this part, we have the fast Fourier transform spectrometers that are used to process all the signals that receptors can detect in the camera. With this spectrometer, we can observe the rotational spectrum in the Q band from 31 to 50 gigahertz and in the W band from 75 to 116 gigahertz of all the molecules that we can introduce in the chamber. When we want to study the rotational spectrum of a given molecule, what we do is to fill the camera with the sample that we want to study. The typical pressure is around 710 to -3 millibars, and we work in a continuous flow. That means that we are injecting the sample, and at the same time, we are evacuating using the vacuum system, just to avoid decomposition problems of the sample inside of the camera. The measurements are usually done at room temperature, or we can heat the camera, the chamber, up to 350 Kelvin, so we can measure vibrational excited states as well. And usually we work with gases and liquids, but we can observe the rotational spectrum of solids with high vapor pressure. The camera is equipped as well with 4 UV lamps that are emitting at 183 nanometers, and they can be used to the study of photodissociation processes inside of the chamber. And also we can produce cold plasmas using a coil connected to a radio frequency source. These are some of the molecules that we have studied using the Gacela experimental setup. All of them are molecules that are candidates to be observed in the space. For some of the molecules, the rotational spectrum was observed before, like is the case of ethyl methyl sulfide. This molecule was investigated up to 26 gigahertz in 1981 by Adachi et al. And these are the rotational parameters determined in this experimental work. If we want to do astronomical search of this molecule, we need frequency predictions in the range of 3 and 2 millimeters. That means in the frequency region from 75 to 116 gigahertz and from 130 to 180 gigahertz. If we use these constants to get the predictions, we get the frequencies. These are the frequencies for 4 of the most intense lines in these frequency ranges. But the uncertainties of these predictions are very large, close to 10 megahertz for lines in the 3 millimeter region and more than 40 megahertz for 2 millimeter regions. So that makes impossible to do an astronomical search because we don't really know where the lines are. But we did the study of this molecule in the range of 75 to 116 gigahertz, and we were able to observe more than 400 rotational transitions for each of the two conformers, the anti and gauge conformers. We also observed the vibrational site states that it's important to observe and characterize the vibrational site states because they contribute also to our astronomical observations. These are the data that we derive from our analysis, and as it can be seen, the rotational constants are almost similar, but the uncertainties are much smaller, close to 2 orders of magnitude smaller than those reported in 1981. Using these rotational and centrifugal distortion constants, we obtain accurate predictions in the 3 millimeter frequency range. The uncertainties are close to only 10 kilohertz, and in the 2 millimeter region, the uncertainties are close to 60 kilohertz. Our predictions are accurate enough up to 250, and using these predictions, we were able to do an astronomical search in 2 objects, Orion and Sagittarius B2, using our data from the 30-meter telescope, but we couldn't observe any of these species in our astronomical searches. However, all the parameters determined in this work can be used or will be used in a future search in these sources or in other objects. A similar work done using Gazella is the study of the cyclopropane carboxaldehyde molecule. This molecule has also 2 isomers, and in the picture you can see a small region of our spectra observed with Gazella. As you can see, there are a lot of lines. They are coming from the trans isomer for the ground state and also for 2 vibrational states, and also in here we can observe rotational transitions for the cis isomer. After the analysis of our rotational data, we were able to identify the ground state of the trans isomer and 11 vibrational states for this isomer. The accuracy of our constants, our experimental constants, is good enough to have good predictions, and even for the cis isomer, where we detect the ground state, and the observations were limited to 6 vibrational site states. With these parameters, we obtain good predictions up to 300 gigahertz, and then we carried out an astronomical search in the same objects, in Orion and Sagittarius, but we couldn't observe any of these species in our search. Another type of experiments I do are dedicated to the generation of unstable species, molecular species with astrophysical interest. With unstable species, I mean all the chemical compounds that cannot be synthesized in a laboratory using organic or inorganic chemical routes and then storage in a bottle. Okay? If we want to observe the rotational spectrum of unstable species, we need to generate them in situ at the same time that they are characterized in the gas phase. To do this kind of experiments, we use the FT microwave spectrometer of Professor Endo in the NYCU University in Taiwan, and this spectrometer is completely different from Gazella. It consists in a vacuum chamber with 2 spherical mirrors, and on the back side of one of the mirrors we have this device that is an electric discharge nozzle that can be used to generate unstable species in the gas phase. Prior to run any experiment, we need to prepare a gas mixture of a buffer gas that usually is argon or neon. And then we have to choose the chemical precursors to synthesize in the gas phase the new molecules that we are interested in. The experimental sequence starts with a gas that crosses this section, this region. The gas passed through a very small nozzle or hole with less than 1 millimeter of diameter. And when the gas is crossing this part, we induce an electric discharge between two electrodes, and this discharge starts the chemical reaction between the chemical precursors that we have in our sample. Then the molecules, the new molecules go into the camera, and they form a supersonic expansion because there's a big difference between the pressure inside of the cavity, close to 10 to minus 7 millibar, and the pressure of the gas. The supersonic expansion is a collision-free environment and is perfect to measure the rotational spectrum of unstable molecules because due to because there's no collisions, the molecules are stabilized. So when the molecules are inside of the cavity, they are proof by microwave spectroscopy. We detect the molecular emission and we obtain the rotational spectrum in the frequency domain. This experimental sequence takes only 40 milliseconds. So the philosophy of this experiment is repeat 100 or 1,000 times the same cycle to get a good signal-to-noise ratio spectrum for the analysis. This is one of the molecules, unstable molecules, that we have identified using this experimental technique. The name is 1-cyanopropyl radical. This molecule cannot be obtained commercially, of course, and it was prepared in gas phase using a mixture of methyl cyanide and acetylene in these proportions, both diluted in argon. We were able to observe a total of 12 rotational transitions, and here you have an example of 2 of them. As you can see, each rotational transition is split in many hyperfine components because this molecule is a radical with 1 free electron that interacts with the nuclear spin of this nuclei, with the hydrogens and with the nitrogen. And that's why each rotational transition appear with many hyperfine components. The analysis of this type of spectra is not trivial, but if we can get a good fit or a good analysis, we can get a list of molecular parameters that describe perfectly these hyperfine patterns. The comparison of the experimental determined constants is with those predicted by ab initio calculations allow us to identify this molecule in the gas phase. Then, as we do with other molecules, using these experimental parameters, we predict at the observational range the rotational transitions, and we compare with our observations. This is an example. In red we have our predictions, and in black is the line survey on the molecular cloud TMC1 that was obtained with the Quixote line survey. And in this case, we cannot conclude that this molecule is in TMC1 because there's not a coincidence between our predictions and the observations. Another molecule that was formed using electric discharge and characterized with FT microwave spectrometer is the deuterated species of the H2-CCN radical or cyanomethyl radical. This molecule was identified in TMC1 in the 90s or in the 80s and is one of the most abundant species in the interstellar medium. So we wonder if the deuterated species of the radical could be present in TMC1. So we ran the same experiment using methyl cyanide and deuterium diluted in argon, and this is a part of the spectrum that we observed. This is the 101000 transition, and as in the other case, it appears split in many hyperfine components. From the analysis of the spectrum, we obtain these molecular parameters that with very, very low uncertainties, and the comparison with the theoretical data is also good. Using our experimental parameters, we make the prediction for the next rotational transition that appears close to 38 gigahertz, and we directly compare with our observations from the Quixote line survey. In this case, we can reproduce perfectly some observations in the region of 37 gigahertz, and this allows us to claim the detection of this molecule in TMC1. And to finish, I show an example of how to detect new molecular species in the interstellar medium using only quantum chemical calculations. The spectra from this figure show two groups of lines that were observed in the molecular cloud L4A3. All these lines were not assigned to any chemical species, and the hyperfine pattern indicates that all these lines could come from a molecule that is a radical. From the relation between the frequencies, we derive value for the B plus C, that are two rotational constants, B plus C over 2, around 36.1 gigahertz. So this number gives us some information about the geometry of the molecule. Using quantum chemical calculations, we predict this value, or B plus C over 2, for all the candidates that we believe that could be the carrier of this group of lines. As you can see, the most promising candidate was the radical H2NC, whose value is very close to the one determined from our observations, but the conclusive identification of this molecule cannot be done only comparing this data. So we need to analyze all the observed lines, as we do when we have a spectrum in a laboratory, like if was observed in a laboratory experiment. So from the analysis of all these lines, we determine all these rotational parameters that perfectly reproduce our observations in this molecular cloud. Then the comparison with the theoretical data allowed us to identify this radical H2NC as the carrier of these lines. This is an alternative method to identify new species in the interstellar medium when we don't have the laboratory data necessary to compare with astronomical observations. And this is the case of H2NC, that is a high energy isomer of this radical H2CN, this one. And this radical has never considered in any laboratory or astrophysical investigations on the only way to detect this molecule in space is by quantum chemical calculations. We have applied this method to identify other species in TMC1, like these cations or a negative ion, also the radical HCCS+, and metallic species in another source, like IRC 10-16, that Luis talked about before, and these four radicals and this molecule that is a closer species. And that's all from my side. Thank you very much.